Hey folks, welcome to this episode on Hydrate Formulas. So let's go back and remember what a hydrate is. It's just a compound that has a specific number of water molecules bound to it. So that ratio doesn't really change. In this case, when we have magnesium sulfate, we have 7 water molecules attached to it, and it goes into various configurations. So what we can actually do is we can actually figure out what this formula is by actually just evaporating these water molecules off, collecting them, and weighing them. And so this is what it would look like. In this case, we're dealing with copper sulfate or copper 2 sulfate. We boil it, we collect the water, and we weigh it. And then we can figure out the ratio between this anhydrous salt and the water that's attached to it. Now again, that's called anhydrous salt, which means that it did have water attached to it, but now the water has been boiled off, evaporated, and now it's just the ionic compound. So we can do two things. We can look at the percent composition of hydrates, and we can also figure out the empirical formula of hydrates. So we're going to start off with percent composition. Now, to figure this out, it's the same thing that we've been doing before in terms of percent composition. What we do is we calculate the mass of the total compound, calculate the mass of the individual items, and divide them individual by the total, times it by 100, and we get a percentage. When we're doing percent composition before, we were looking at individual elements. However, when we do percent composition for a hydrate, we look at just the ionic compound, CuSO4 in this case, and the water. Instead of breaking it up into Cu, S, O, H, and O, we just look at this one compound and the water. So it makes things a little bit easier. So in this case, we have 3.72 grams of copper 2 sulfate pentahydrate. Calculate the mass of the water contained in the sample. So this is actually a two-part question. This mass actually has nothing to do with the percent composition. It's simply a sample size, which we first have to figure out what percent does water make up in this compound here of copper 2 sulfate pentahydrate. Once we figured out that percentage, then we can apply it to the sample and figure out how much water is in the sample. So let's go ahead and do this. First things first is let's look at creating the total mass of the copper 2 sulfate pentahydrate. So the molar mass of CuSO4 pentahydrate 5H2O, if we do everything, we multiply 18 by 5 because there's 5 water molecules, we'll get 249.61 grams per mole. So that's our total mass of our entire compound. So what we're going to do is just split it up. CuSO4 and H2O. Remember how we were doing percent composition before? We took all of our individual elements and we split them up over here. But again, we're just splitting up the ionic salt with the water. So we're going to find the mass of each. And again, looking at our periodic table, we know we have one of these, and this weighs 159.61 grams per mole. So that's going to give us 159.61 grams per mole. I'm just going to erase that little dot there. Let's get rid of that whole thing here. 159.61 grams per mole. Now in water we have 5 of them, and each one weighs 18.00 grams per mole. So we're going to get 90 grams per mole. Okay, now again, if you mass these up, then you'll get to 249.61. So to figure out what the percent composition is, I take both of these values and I divide it by the total. Okay, so in this case, it's going to be, I'm just going to use the red here, 249.61 grams per mole, and again, 249.61 grams per mole. Okay, so my grams per mole will cancel out, and the last thing I need to do is just multiply by 100, and I should get a decimal. Now we're going to keep it to 2 decimal places, even though our sig figs might not line up. It allows us a little bit of flexibility. So once I do that and I multiply by 100, I'll get 63.94% CuSO4, and in this case I'll have 36.06%. Now you have to make sure that they do add up to 100%, and in fact they do. So here what we've just discovered is that 36.06% of the total mass of this compound is made up of water. So that proportion is pretty much the same. We could have 1,000,000 grams, we can have 0.001 grams, whatever. The proportion will always be the same. 36.06% of any sample will be made up of water. So what we're trying to figure out is this sample here, how much is that made up of water? So all we do is we take 3.72 grams, and we multiply it by this percentage. I'm just going to turn it into a decimal, 0.3606. And what I get here is 1.34 grams of H2O. So this sample, it has 1.34 grams of water in it. So try this one yourself here. Here you have a 78.34 gram sample of calcium chloride dihydrate. So again, figure out what the formula is first. And then once you figure that out, you have to create the percent composition of the calcium chloride and the percent composition of the hydrate. In this case, there's 2 water molecules attached. Once you figure out the percentage of water, you can then multiply it by the sample that you have over here to create your final answer. So go ahead, pause it, see if you can figure it out, and we'll come back with the answers in a few moments. So here are your answers. We have calcium chloride, CaCl2. Remember how we create that formula, CaCl. This is 2 plus from our periodic table, and this is 1 minus. We cross, we get CaCl2. And dihydrate means there's 2 hydrates. So if we figure out what the total formula, the total mass is, 146.98. We found out what the mass of calcium chloride is, it's 110.98, and water, 2 times 18 will be 36, divided by the total mass, and multiply it by 100, and you get a percentage that also equals up to 100%. So here, 24.49% of the total mass is made up of water. We multiply that by our sample size, and we get 19.18 grams of water. So that's percent composition of hydrate formulas. Let's look at creating empirical formulas. Now, we're usually given this anhydrous salt, and we're saying that it's hydrated. But that just means that there's waters attached to it. We don't know how many. It doesn't say dihydrate or pentahydrate. It just says that it's hydrated. So when we were doing our empirical formulas, what did we do? Well, remember that we figured out how much of each we started off with. It was sometimes given as a percentage, and we assumed 100 grams, or it was given as grams. Let's save this that first step. The first step was converted into moles using the molar mass of each compound. Once we did that, we had to create that ratio, and we divided all numbers by the smallest number. We created that ratio, those became the subscripts. Now in here, that ratio will actually be the coefficients because we're dealing with compounds instead of individual elements. So it's very, very similar to the ones that we've done before. We're just applying it in a little bit of a different context. So let's take a look at here. A chemist heats a 300 gram sample of hydrated iron 3 nitrate until all of the water of hydration is driven off. The anhydrous, or the dry compound, is found to weigh 179.7 grams. What is the correct name of the hydrate? Okay, so sometimes it actually helps to draw what's going on here. I'm just going to make this a little bit smaller here, just so we have a little bit more room to work with. Now, our hydrated compound, it just says hydrated, it doesn't say how many waters are attached. Iron 3 nitrate, so that's Fe bracket NO33, and it's attached to a certain amount of waters. We don't know what that X is. That's what we're trying to figure out. Now this whole compound weighs 300 grams. Now when we heat it, the anhydrous, FeNO33, is separated from the water that boils off, H2O. Now it says that when we weighed it after we heated it, that anhydrous compound weighed 179.7 grams. So how much does the water weigh? Well, if you remember the law of conservation of mass, the reactants should be the same as your products. Now there's not actually any reactants for products here, because this is a physical change, but we can see that what the mass should equal. So what we do is we just take 300 minus 179.7 grams, and what we get is 120.03 grams of water. So here we have our starting point. We have our starting point of our anhydrous salt and our starting point of our water. So let's set up our empirical formula. We're going to put our compounds on the left side. So Fe bracket NO33 and my H2O. So my starting here is 179.7 grams, and my starting with the water is 120.03 grams. Again, this should just be 3. So, how do I go from grams into moles? Again, what you need to do is you need to divide by the molar mass. So in this case, I want to get rid of grams, and I want to be left with moles. So grams per mole is my molar mass. Molar mass of what? The thing that it's representing, iron 3 nitrate. So in this case, the molar mass of that is 241.88. And so my grams will cancel out, and what I'll get is 0.744047 mole. We don't round until the end, so I'm just keeping this really, really big number here. Now let's do the same thing with the water. We're going to multiply by its, or divide by its molar mass, 18.00 grams per mole. My grams will cancel out, and I'll be left with 6.668333 mole. Alright, so here we have two mole values. We have to see which one is the smaller one, and it's pretty obvious. This is a decimal here. So what we're going to do is we divide both of them by that number, 0.744047 mole. And by doing so, our moles will actually cancel out, 744,047 mole. Now in this case, this is going to be 1, and this is going to be equal to 9. So these numbers now actually represent our coefficients. Here, what this says is I have 9 water molecules, and I have 1 formula unit of FeNO33. So if I put that together, I have 1 Fe bracket NO33 dot 9H2O, but again, we know that we don't write the ones, so it's just going to be Fe bracket NO33 dot 9H2O. The question's asking us what is the correct name, so this would be iron 3 nitrate nona hydrate. And that's it. Now let's look at this one. A hydrate of iron 2 sulfite is known to contain 44.26% water. What's the correct formula of the hydrate? So in this case, we're actually given a percentage. Again, I'm just going to make this a little bit smaller to give us a little bit of working space. Here we have a hydrated iron 2 sulfate. So iron 2 sulfate is just FeSO3, and it has some amount of water attached to it. Now if we boiled it off, we would get FeSO3, and we'd have H2O. Now the question states that we have 44.26% water. And that's a 6 there. How much FeSO3 do we have? Well, it's actually pretty simple. If we know that percent composition is always equal up to 100, we can just do the reverse. 100 minus 44.26. And what does that equal to? That equals to 55.74%. Now again, we don't have any direct conversion from percentage to moles, but remember that if we assume we have 100 grams of sample, this makes things a lot easier. So we have FeSO3, we're just setting it up for ourselves here, and we have H2O. What we see is we have 55.74%, but if we assume that we have 100 grams, well, that means that we have 55.74 grams of FeSO3. Same thing with the water. Here we have 44.28%, and that means I have 44.28 grams of water. So our first step is to get into moles, so we divide by the molar mass. In this case, we have 135.91 grams per mole, because that's our molar mass from our periodic table. And here we have 18.00 grams per mole. Our grams will cancel out. And what we're left with here is 0.410124 mole. And here we have 2.45884 moles. So once again, I need to figure out which is my smallest value. That's a very obvious choice. It's this one over here. So I divide both values by that smallest value, 0.410124 mole. My moles will cancel out. Again, 410.124 mole. And what I'm left with here is 1, and here I'm left with 6. So these become our coefficients. We don't write our 1s, so our final formula is FeSO3 dot 6H2O. So try this one yourself. Again, make sure you can sometimes draw those drawings. That really helps you kind of see what's going on. A crucible, remember, is just a little ceramic thing that we use to heat things up very, very high. Anhydrous is, again, salt without any water. And cupric sulfate, if you haven't seen this before, cupric is just another way of saying copper 2. If you had copper 1, it'd be cupros. That's just an old stock way of naming things. So don't get caught up in those little details. Try to figure out what the correct formula of the hydrate is. So we'll come back in a few moments with the answers. So once again, here we go. We know that it's a hydrated copper 2 sulfate. We don't know how many hydrates we have, so it's just X. Once again, here we start off with 500 grams of this hydrated copper sulfate. This would be 500 grams here. And we saw that 180.35 grams of water were released. So we knew that value right away, but we need to figure out what this value was. Again, law of conservation of mass. We just subtracted these two, and we got 319.65. We divided by the molar mass of each of these to get a decimal place here. And we divided both by the smallest value. In this case, was 2.002694 mole. And we got a ratio of 1 to 5. So the 1 went in front of the copper 2 sulfate, the 5 instead of in front of the water, and we got copper 2 sulfate pentahydrate. Alright folks, that's all for now. Thanks for watching. See you soon.